Are we ready? Okay. Good afternoon, everyone, and welcome to the College of Optical Sciences Colloquium series. You have this weekly, and it's my pleasure to introduce our colloquium speaker today, Professor Rolf Binder. So he's local. He also has a joint appointment with the Department of Physics, right? So Professor Binder studied physics at the universities of Dortmund and then Stuttgart, I think. He received his PhD in theoretical physics from the University of Dortmund in '88, and then he joined U of A in '89. So it's been quite a long time been here. Professor Binder is also a fellow of the Optical Society of America. His research focuses mainly on the analysis and application of optical properties of solids using a variety of theoretical formalism, including non-equilibrium Green's functions. So examples of recent research projects include electromagnetically induced transparency, optical and elastic properties of semiconductor nanomembranes, and optical properties of graphene. So he's here today apparently to get help with his zebra in the quantum flute. So I hope that you will join me to welcome Professor Binder, and let's see if we can give him help.
Yeah, thank you very much, Khan. I would like to thank Khan for this nice opportunity that he gave me. I would like to share with you, of course, some of the work that we have been doing over the past years. But one other thing I want to try to do, I want to share with you the enthusiasm that I have for the field that I'm working in, which is semiconductor optics. If you work in semiconductor optics, you are forced again and again and again to learn about stuff that has nothing to do with semiconductors. And that's a good thing. And sometimes the world around you may say, oh, semiconductor optics, that's really not all that glamorous. But on the other hand, what you learn when you do this is how the world around you works. And that it can actually be very rewarding in the long term, I think. And so, yeah, many of you know that I'm a theorist. I don't do experiments. Except when I wrote down this strange title, this was an experiment to see if I can get more people in the audience. So here's the real title. On the effect of four-particle quantum correlations on spinor-valued exciton polaritons and the spatial structure of four-wave mixing signals in semiconductor microcavities. You like this? Or you like the first title better? Okay, let's stick with the first title, okay? Yeah, let me start with the acknowledgements. In my group, the people who contributed most to the stuff that I will talk about is Nai Kwong and Samuel Luke. He's a graduate student currently, and Bai Jae Gu. And so we have a number of collaborations, outside collaborations, in particular with Stefan Schumacher in Paderborn and his students. Stefan is on sabbatical. He's actually here in the room. And the experiments that I will show were done in Paris in the group of Jérôme Tignon and Emmanuel Baudin. And part of the theory was contributed by our collaborators in Hong Kong, the group of P.T. Leung. And some earlier work was done together with Makoto Gonokami. So what I want to do is I give a relatively extensive introduction to semiconductors and many-particle theory, and then talk about four-wave mixing. That's the basic process that we have to consider in this talk. And then, of course, about patterns in these polaritonic quantum fluids. And if time allows, I will talk a little bit about one of the more formal aspects we have been working on, namely this dipole matrix element. Many of you may have seen the booklet that Masoud Manzouri put together. It's a really nice booklet. It's actually about us, the optical sciences, the College of Optical Sciences. What do we do here in terms of research? And I really like the booklet that he put together. one has to say that there's at least one author who contributed a chapter, redacted here, with a kind of pretentious title, The Universe of Semiconductor Optics. What does that mean? And the first sentence is even more annoying. Semiconductor optics is everything. And then it goes on and on. Like, chemists can work with hydrogen atoms, but can anybody actually make hydrogen atoms? And then when the laser beam hits the semiconductor, it's a little bit like the Big Bang, because we basically create a certain kind of matter inside the semiconductor, but, okay, admittedly, it's more like a small bang. So some of the areas that you automatically come in touch with when you are working in semiconductor optics are listed here. Not all of them, just a few examples. And as we go through the talk, you will see I will touch on some of those. Quite a variety, from communications technology to chemistry to ecology. And pardon me? Zoology. Thank you. I forgot that. Thank you. Pardon me? Good point. What can I say? I said it's not complete, did I? Okay. This is pretty much complete. This is all we can handle. I have a small group, so some of the group interests that we are currently working on. This, of course, is part of the talk. Graphene, we work a little bit on graphene, gallium arsenide nanomembranes, and also we have a project with one of the local companies here, RTA, where we work on green lasers. Let me start out with some weekend experiences with perturbative and non-perturbative two-particle correlations. Okay, so what do we do on the weekend? If we don't go to the zoo, we play billiards. Oh, no. I don't know. Okay, sometimes the billiard table is not very good. So then we have bound states, okay, non-perturbative. Okay, let me talk about semiconductors for a little bit. So if we have a crystal, an array, or lattice of atoms, basically each atom can be thought of maybe have two energy levels. Same for each atom. When we bring them closer together, that they really form a crystal, then the energy levels kind of the degeneracy is lifted, and we have energy bands. In reality, this looks a little bit more complicated. We have this kind of terrible-looking band structure, say, for gallium arsenide. Luckily, we don't have to worry about all of this. We just look at the little part around this gamma point, and that's all we have to worry about when we do optics, anyways. And so there we have a valence band and a conduction band, okay. In the ground state, the valence band is full of electrons. Okay, so if the light field comes, it creates an electron, or it puts an electron up in the conduction band. It leaves a hole there, hole, light absorbed, hole in the valence band. We forget about the electrons in the valence band. We just say it's a hole in the valence band. It's good enough for the description. So we have an electron and a hole. Hole is positively charged particle, and electron, of course, negatively charged particle. So then we have an electron-hole pair with charged particles that can form bound states via the attractive Coulomb interaction. The bound states are basically like the ones that you know from the hydrogen atom, basically. And then we have continuum states. So excitons in this regime would be like this. We come in with a pulse, and then they do whatever they want to do. Sorry. Okay. We can also have with a little bit more complicated excitons in equilibrium with an electron-hole plasma. That would be actually quite a bit more complicated, because this is like a partially ionized, or in analogy, you can see that to a partially ionized hydrogen plasma. So you have hydrogen atoms and hydrogen plasma, and that's all in equilibrium. Then this is a little bit more complicated. And we have worked on this for some time ago. In particular, we have looked at excitons in equilibrium with the electron-hole plasma and looked at the excitonic luminescence in a so-called heat matrix approximation. So that is something which obviously borrows from chemistry there, because I'm talking about chemical terms here. Let me do a little bit of introduction to many particle theory. And this is kind of terrible. This is probably the most terrible slide. After that, it will get better, I hope. So when we describe the system, we start out with the Hamiltonian. And the Hamiltonian is, in principle, very simple. We have a Hamiltonian for the bands. I just showed you 2 bands. We have a Hamiltonian for the Coulomb energy, which gives this kind of bound states, and we have the light coupling. And I'll show you how this Hamiltonian looks, and then I will basically forget about that. Everybody, half of the audience here knows that anyways, and the other half will get some feeling for what we are doing. I see we have a lot of students here. I mean, I teach, this semester I teach Opti 370, what is it? And I'm glad there's quite a few students from Opti 370 here. I also teach Physics 561, and there's also students from Physics 561 here. Very good. So the band Hamiltonian is pretty simple. We have electrons and holes with equation numbers indicated there. The Coulomb interaction is not quite so simple. We have these 4 operator terms for electron-electron, hole-hole, electron-hole interaction. And then the light coupling is semi-simple. It has the light field amplitude E involved, and then operators for the electrons and the holes. So basically electron-hole pair creation and annihilation operators. So this Coulomb interaction, they correspond to this kind of scattering between the particles. Here for the electron-electron, and then we have corresponding for the hole-hole and so on. And then for the creation of the electrons, we have the pair creation operators. As I said, if time allows, I will talk a little bit about this matrix element, because that's kind of a difficult subject. What I want to talk about in the following mostly are 2 exciton correlations, and everything, all the zebra stuff will be based on these 2 exciton correlations. And so the way I can kind of visualize them with the help of Bill Gates here is like this. So obviously this is not a quantum description, but the basic point is that we have 4 particles that all interact with each other and basically can be classified as 2 pairs of particles. We could also have continuums interactions, a repulsive interaction, and then it looks a little bit more boring. Like this. That is actually much simpler to treat, and so many of the examples will fall into this category of repulsive exciton-exciton interactions. One slide again, this is a little bit kind of terrible because it's a little bit more formal. So how do chemists treat like binding of 2 hydrogen atoms? They write down what we call the Heidler-London model. They say, well, we have one hydrogen atom or one exciton here, one here, and both is in one state, for example, the ground state. And then we still need to account for the fact that each particle interacts with each particle, and then we can get the total Coulomb interaction energy that could give us, depending on the spin state of the system, bound states, or it could not give us bound states. But that is what chemists do. And so we did this for excitons, which is a little bit more complicated, but conceptually the same as what the chemists do. We have electron-hole creation here, and then we have Coulomb interactions. I show only one example here, and so we can actually have exchange interactions. So the electron, one electron interacts with the other electron, and so the pair that comes out has, in this case, kind of the wrong electron that comes in here. So those are the processes, or that's the theory that will be underlying what all of what I will say in the following. Just to kind of summarize, so this slide here. So we have worked on these exciton interactions with frequency and spin-dependent interactions, and we have applied this infinite ladder summation. So we do it a little bit more sophisticated than the perturbation theory that you know basically from chemistry books. So we actually sum up excitonic ladder diagrams. And so these diagrams that you just saw, we have worked out quite some time ago. So let me talk about 4-wave mixing. What is 4-wave mixing? Let me talk about 4-wave mixing first from the point of view of wave mixing. As the term implies, we have wave mixing. And the waves are, of course, our optical waves that come in. So what I'm doing here is I show like a pump wave, and then I depict like the phase fronts. And so that would be the pump wave, and I put two arrows here to indicate it's kind of a strong pump wave. And so then we could come in with a probe, which I call signal here, but at an angle. And you see what happens here. We get these kinds of grading thing. Like there are certain points in space where you have a lot more intensity, and therefore a lot more excitons, and therefore a lot more exciton-exciton interaction than at other points. So this grading itself then can act to actually diffract. So the grading period would be in this nomenclature, K pump minus K signal. And so what this can do is the pump itself can be diffracted off this grading and go into a new direction. So that is kind of 4-wave mixing in its simplest form. From a wave mixing point of view, and maybe that's what you are used to when you think about holography or things like that. Just a wave. I actually like to think in terms of 4-wave mixing differently, because I like this billiard analogy. I like to think that we have two pump beams that come in, they make excitons, and the excitons scatter off each other. So I like to kind of view it like this. So this is my way of depicting 4-wave mixing. Physically, there's no real difference here, but I say, well, we have a pump, photon come in with wave vector Kp, and another one with another Kp, and then the two outgoing excitons could go into the signal direction, and one could go into the 4-wave mixing direction, which is 2 K pump minus K signal. So it's kind of two different points of view. One has each has its positive and its negative sides. There's a little bit more to 4-wave mixing, actually, and that is this. Let's think about 4-wave mixing. And so in this case, I actually think about a pump coming in. One comes from this side, and the other comes from this side. So again, it's just two arrows coming in. And then we come in with a probe, like before. We make this grating, and now we come out with a 4-wave mixing signal. But in this case, the 4-wave mixing signal actually doesn't come out this way; it comes out this way. Big deal, you would say. Well, coming out this way or this way. But there is a difference. Now, K 4-wave mixing is just minus K probe. So say you have some K 4-wave mixing. So you have some 4-wave mixing signal to begin with. Okay, let's do this again. We have our pump beams, and say now the input is a 4-wave mixing signal in this direction. Okay, we have a grating made with a pump and a 4-wave mixing, and now the diffracted beam, the 4-wave mixing of the 4-wave mixing, goes in the original pump direction. Do you see what that does? We have a pump wave and a signal wave. We do wave mixing, we create a 4-wave mixing wave. Then we have a pump wave and a 4-wave mixing wave. Obviously, we do wave mixing, we have a signal wave. And so on. So the system accelerates kind of itself. There is a possibility of instabilities, that you get more and more scattering. Because whenever you create 4-wave mixing, you create more signal wave, and more signal wave means more 4-wave mixing. So let me talk about microcavities now in polaritonic quantum fluids. And for that, I first have to talk about the system that we are looking at. And the system is a semiconductor microcavity, which has two mirrors. In this case, these distributed back reflector mirrors, DBR mirrors on each side, and then there's a quantum well in the middle. And these mirrors act just like the Fabry-Perot that we did in Opti 370, like a few weeks ago. So there's really nothing much more to say about, except that now we allow for the light inside the cavity not only bounce back in a normal direction, but go with a certain in-plane wave vector k in the direction of the travel in the direction of the quantum well. So that leads to some interesting phenomena. If you look at the light dispersion, in the simplest way, you remember light dispersion in 3D, omega is c times k, and that's it. Okay, but if we are in this cavity and we look only at the light dispersion in this cavity, well, you would say, well, without any k in plane, the frequency of the light is fixed. It's the cavity mode. But if you go along the in-plane direction, well, the frequency increases a little bit, but it increases like c times k squared, that's in-plane squared, plus this fixed number. And so this curve is actually not just a linear curve. It's this kind of curve that is indicated here in the magenta color. And so that is our photon dispersion now. It has a minimum there. And then we have the exciton itself. The exciton also, it's just a particle. It has some mass, some mass m. So the energy of the particle would be h bar squared k squared over 2m if it travels inside the quantum well here. But the mass is so heavy that I should have drawn here like a parabola, but I didn't do this. I just draw a flat thing because the mass is basically infinite. So it's really no dispersion left on this scale anyways. So the next step is we have to couple these two, and these are coupled obviously because the material polarization couples to the light and vice versa. So this shows the coupled modes. We start out with two modes here. We get two coupled modes. One we call the lower polariton branch here. One we call the upper polariton branch here. And the lower polariton branch looks kind of nice here. It's a it corresponds to a particle with a very small mass. And so that is really what we are working on in the following. So these polaritons that we can generate here, these form the quantum fluid. Quantum fluid meaning these are just particles that kind of move freely, almost like in a gas, but of course they interact. I should mention this area of polariton physics. It's a huge area, and there's like hundreds, maybe thousands of papers out there. I still want to list here what I think could be listed as the milestones, but that's kind of a personal thing. You can probably disagree with me here. So I would say one starting point was spectroscopy of bosonic interactions in the 1990s by Gonokami. And then there was this parametric amplification using a magic angle by Savidis et al. In 2000. And then there was Bose-Einstein condensation of these polaritonic particles in 2006. And recently they have one group, the group of Bhattacharya, have published a paper where they say they demonstrate room temperature Bose-Einstein condensation of polaritons. Polaritons so have certainly attracted a lot of interest. So whether or not you agree with all of the papers and all of the papers' conclusions is up to you. But this is probably what these are some of the papers that kind of drove the field and kind of made it larger. So this is our system now. Oh, and I forgot to say, so I listed here in the last slide, the first author on this review article, Hui Deng, she's in Michigan, and she will come here to give the colloquium, I think April 16th here. So if you want to learn more about, I don't know what she will talk about, but anyways. So this is our scenario here. So we have this lowered polariton branch, and we pump it actually not on the polariton branch, but we pump it at k equals 0, which means normal incidence. We just come in with a light beam in normal incidence, and then the pump photons via these interactions, these kind of four-wave mixing interactions that I indicated before. Two pump photons can actually scatter on the polariton branch here, like indicated here. And so what that can have as a consequence then is that if you look, for example, at the reflected beam can have these patterns, and this would be a hexagonal pattern, a 6-spot pattern in the far field. And if you would look what happens in the exciton density inside this cavity, so here's a quantum well somewhere. This is a dBr mirror. This is a dBr mirror. Here's a quantum well. The spatial exciton density would have this kind of I don't know if you can see this very well. It looks like a hexagonal lattice. So of course not infinitely extended because the beam has a certain size, like a few tenths of microns or so. So it's not infinite in size. What is relatively easy to observe for our experimental colleagues is the far field pattern. That's the most easy to observe. So this can happen, and we want to get a better understanding of this. Well, before I come to this. So patterns. I should say one thing. You may be aware that here at the University of Arizona, we actually have some of the, how should I say that, the world's foremost experts on patterns. They're in the math department. Above all, I would probably say Alan Ewell. He's really on top. He has an equation named after him. So what else can you want? And he really knows everything about patterns. So from the point of view of the mathematicians, what we are doing here is probably a kind of on the easy side, but for us it's enough to understand what is going on in our experiment or in our theory. And so I will not go to the very height of what is possible in terms of mathematical formulation of pattern theory. Okay, let me talk about patterns from this point of view. This is the original Turing pattern. There's something like Turing patterns. And yes, this is the guy from the movie. I still haven't seen the movie, The Imitation Game. Who has seen the movie here? Oh, everybody. Everybody goes to the... Now I know why they are late with the homework all the time. A lot of people have seen the movie, The Imitation Game. I haven't seen it. Alan Turing is a very kind of, it's a very tragic story actually, and I will not go into this. Watch the movie. But anyways, this is the guy, and so he wanted to know how patterns come about. And he wrote one paper only on the subject, a chemical basis of morphogenesis. And he kind of invented the computers conceptually, but he had to do this, he said actually, by hand, for a few hours by manual computation. He came up with this pattern. Okay, it doesn't look like, looks more like a cow than a zebra, but it's kind of amazing. Now here's a zebra finally. There's a famous quote ascribed to Turing, they say he said the following, roughly the following: well, I can understand the stripes relatively easily, but what about the horse part? What about the horse part? Why does the zebra look like a horse? Why do we, the people, look like we look? That's what he really wanted to do. I mean, he was after nothing less than life itself. It's an amazing thing. And it was in the early 1950s. So, for example, we run around with stripe patterns all the time. But how are they generated in the embryonic stage when we don't have any structure? Okay, so that's what he really wanted to know. What about the horse part? Okay, there's all sorts of stripe patterns. For example, you don't think about it necessarily all the time, but the fact that the heart is on the left is a stripe pattern. It breaks the left-right symmetry. We have one stripe here and one stripe there. And so, obviously, I'm not an expert in biology. As far as I understand, the people really still try to identify this Turing pattern mechanism for example, why do we have like 5 fingers on a hand? It seems to me it's easier for them to identify the genes that triggers that rather than the actual Turing mechanism. So what is this Turing mechanism? So he had in mind some chemical reaction, but his model was taken over by many areas of science, in particular predator-prey models in ecology. So I wrote down here like the rabbit and fox model in a linearized version. So chemically speaking, we are talking about an activator-inhibitor system. And I like the thing with rabbits, they are activators, they are autocatalytic in the chemical sense, because you know what the rabbits do when they have time. They create more rabbits. Okay, and so that is this term C11 times R. It increases the rabbit population. Of course, when there are foxes around, it has a minus sign. It decreases the rabbit population. And so you can write down this kind of equations. And they also diffuse. And the foxes actually diffuse at a larger pace than the rabbits. And then it is possible that there can be actually stationary patterns in the population. And so there are some mathematical requirements for that we could call it Turing pattern. And I don't really want to go into the detail. I just want to say that there can be stationary patterns in this kind of system. And if we have those stationary patterns, then we would call them Turing patterns. And the next question would be, what about quantum rabbits and quantum foxes? What if maybe I should have gone back to that because I didn't. This is diffusive transport. DDT is like Nabla squared. And so the next, we just think about, well, what if we put an IH bar in front of this? Looks pretty much like quantum equations, right? And so indeed, it could be viewed as a linearization of an equation that most of the graduate students here know for sure, this Gross-Betajevsky equation for quantum fluids. I wrote it down here in a nonlinear form. If you linearize this, you would see that the role of rabbits and foxes could be played by the real or the wave function and its complex conjugate, basically. Our equation for the polariton fluid looks a little bit more. It's a little bit more generalized. That looks a little bit more complicated, but the structure basically is the same. And this V-Hartree-Fock, this repulsive interaction, that is exactly the repulsive two-exciton interaction that gives rise to the excitons that scatter off each other. I should say one more thing here. There's a lot of work on nonlinear patterns in nonlinear optics, and so there's a lot of overlap also between patterns in our system and in optics. What distinguishes them, I would say, is the fact that in nonlinear optics you have the nonlinearities happen at fixed atomic positions, and all that moves is the light wave itself. Whereas here in the quantum fluid you have these quantum particles that are indicated here like wave-like and particle-like. They just move freely through space, they interact, and so via the interaction they can form patterns. And those patterns are typically stripes or hexagonal patterns. Now, what are stripes? Stripes at the simplest mathematical level are very, very simple. Write down e to the ikr, e to the minus ikr. Well, what is it? 2 cosine kr. You plot this. I just plotted it here. This is not a result. It's just really just plotting cosine kr. It's a stripe. Okay, and so it has two, in Fourier space it has two k values, this one and this one, so two opposite k values. Now you can do the same thing. You can, for example, take 6 k values, add them all up, plot what it looks like in real space. Well, it looks like a hexagonal lattice. You see this hexagonal lattice here, for example. You could say, well, maybe two of the spots are a little bit stronger than the remaining 4. You plot this, very, very easy to do. So 2 are stronger than the 4 dots. Then you get something that is kind of in between stripes and hexagons. You see kind of the stripes here, I hope. And then you can still see kind of the hexagon, 1, 2, 3, 4, 5, 6, right? So that's kind of in between. Now, as far as our system is concerned, I said before this excitonic polarization, the Hartree-Fock interaction, that is the repulsive interaction between excitons. And so if you look at our equation, this looks a little bit like this Gross-Betajevsky equation, but now really in our kind of language here. We have a polarization for the exciton, and it's proportional to 3 polarizations of excitons, so it's nonlinear. If we would Fourier transform this is as function of space. We Fourier transform this to know what happens in the far field. Then we see, because this is a product, we get all these convolutions here, terrible convolutions. But so you can imagine that if you have in the far field, you could have these 6 dots and corresponding to different components, Fourier components of the polarization, and so they can all scatter off each other. The question is, well, how do they really scatter, and why hexagons, and why instabilities? I list here a few of those scattering processes. So this, again, is the K space. We have the pump is at K equals 0. 2 pump photons can scatter onto the polariton dispersion like indicated here. This is a basic instability. There's nothing special about this direction. It could be anywhere on the ring. You would just get ring, conical emission on a ring that way. But anyway, so this is one of them. It could also happen that one pump photon and one pump polariton and one on the ring scatter together and create two more on the ring. Now this works only if this is 120 degrees. So this actually favors the hexagons, this scattering process. And then there is one scattering process there where we have like two on the ring initially, and then we create two others on the ring. This we could call either self-saturation or cross-saturation, depending on whether or not the final states are the same as the initial states. And so this is this kind of winner-takes-all term. And so if we have the winner-takes-all, then from the basic instability, we would expect a two-spot pattern or stripes. From the hexagon, we would expect one hexagon, not hexagons in this direction, and this direction, and this direction, but one hexagon will maybe in this direction, even though there's nothing special about this direction. And so this is the experimental setup that our colleagues in Paris used. They used, for some reason that I don't want to go into, a double cavity here. You see they come in with a pump beam in normal incidence. They look what comes out in the far field. So the pump photon scatters on the polariton branches. And the basic result, experimental result, is shown here. We have in a far field pattern, indeed, kind of six spots. In this case, like it's two strong spots and like 4 weak spots. And that by now doesn't surprise you that if you look in the near field, which is very, very difficult, I understand, to do for the experimentalists, you get this kind of, you see kind of these stripes here. But at the same time, you see kind of a hexagonal structure. So that corresponds to the fact that in the far field, you have two strong spots and 2 weak spots. So that's that's the main experimental result. One can kind of control these patterns. For example, if you start out with an hexagonal pattern, if you just build in some anisotropy just by tilting the pump a little bit from the normal incidence, then we favor a certain direction and we go from like a 6-spot pattern to like a 2-spot pattern. Here theoretically it's of course always much nicer, 6 spots to 2 spots, and the 2 spots would correspond then to the zebra in the quantum fluid. What can we do with this? Some time ago, we thought we actually knew already what we wanted to do with this, and this proposal, what we could do with this, was actually based on an earlier paper by the group of Dan Gaither, who did experiments on a gas, on ruby. Well, what was the gas? Ruby, right? Yeah. Not a cold gas, a warm gas. And so we modeled the system a little bit like this. We said, oh, we should be able to do this in a semiconductor. So we said, well, if we have a pump beam and we have all these probe beams and we have initially some output in a certain direction, could we switch it to the other direction? And so switching it is very nice because you have a switch, an all-optical switch in this case. We initially, without the control beam, we have emission in this direction. We put a weak control beam here, and the stress is on weak, and then the whole thing switches over to the other side. A switch is actually very difficult to understand. In particular, if it's a switch that works with a very weak field. It's always easy to switch something that is, if you are the strong, if you say in terms of masses, okay, masses, there's a toddler coming crawling at you, okay, you just stand here. He will not go this way, he will go that way or that way. He for sure will go a different way. He will go out there will be a directional change. Okay, so once you understand the principle, it would be very unwise to think you stand on a track with a train coming at you, and you think, I will just stand here, and the train will go this way or that way. It will not happen, okay? And so switching something which is actually much weaker than what you want to switch is tricky business, Okay. And so we here think we have found a way where one can, in principle, do this. Now, in experiment, it doesn't work quite that well. They do see the switching, but it's so far, and this was their first experiment, I have to say, they do see the switching from this direction to this direction by putting this control here. We hope that in the future they can do this with much weaker control pulses. If the system gets better, we are actually quite hopeful that that works. So why is this interesting? It's interesting from like a communications technology point of view. If you want to build a transistor switch is kind of something big with a very weak control signal, what we call base, maybe in electrical engineering. And so what we have in mind here is, if you look at a certain spot, direction here without the control beam, there's no output here. But once the control beam comes, then there will be output here, and the output can be much stronger than actually the control beam. Hopefully, in reality, in theory, it can already be much stronger, but hopefully in experiment that will work as well. There is more things that you can do with these things. For example, fan-out device. So you start out with your pump, and so when your signal, and you have in the off state, so to speak, just 2 dots here, the signal that you could modulate, you could put zeros and ones on to modulate the signal. Then you come in with one signal, but the output will be in four directions actually, and so that would be an all-optical fan-out. One question is, why does it switch? I can understand, let me go back. I can understand if you put a signal here, there will be some output here, but I cannot easily understand why does it actually switch off in the original direction. Why is there no light left in the original direction? And so we try to learn a little bit about switching in our group. And so I want to share that with you. Consider first some simple homogeneous system, okay? We have, this is our old equation, but only for k equals 0, so only for the homogeneous part, just to make it simple. Since this is a cubic equation, we have the stationary states. You plot the stationary states as a function of this control parameter, which would be the square of the input field, so the input intensity. You get this S-curve. There's an S-curve there. You could actually think that there's like two control parameters, not only the intensity of the input field, but also the Hartree-Fock strength of the exciton interaction. And so if you would plot this curve like as a function of the second control parameter and the first control parameter, you would get these states, and it would look like this fold. This can become a little bit more clear if we look at the same thing, but in a very simple notation. Think you have a particle that has an equation of motion like this with a gradient of a potential, and the potential is this fourth order polynomial. The stationary system would be, the system will always be in one minimum. Okay. Now, depending on the values of u and v, the minimum could be, for example, here. That's the stationary point. But if there are certain values for u and v that allow for two minima, then the system could be here or could be here. This would be bistable. Okay? And then if you go actually back and forth, you may lose or win stable solutions. For example, if you're in this stable solution, you go over this bifurcation line here, then the left solution is actually still there, so you don't feel anything. You go further, but here you lose the left minimum, and you roll over to the right minimum, and that you would kind of call a catastrophe then. So that's the basics of switching. You could call this a non-equilibrium phase transition. Mathematicians call this differently, but let's call it that way because most of us are physicists here. There's actually a nice way of demonstrating this. You need two rubber bands. If you just have two rubber bands, you can build what is called the Zeeman catastrophe machine. And I want to show this here. This is not an experiment. This is it's a theoretical experiment, or maybe it's experimental theory. I don't know if it works. So, oops, I need to push this a little further. So we have a one-dimensional parameter space, which is the position of the wheel, and we have a two-dimensional control parameter space. I can put this up and down, and left and right. two-dimensional control parameter space. When the control parameter is in this segment, I have one stable solution. So I can push here, it's stable. Okay. I can also go to this side. I have one stable solution. I can push here, it's stable. But I could also go here. Oops, go this way. I have two stable solutions, this one and this one. And so now I can actually go from one side to the other and see what happens. So I go this way. Actually, nothing happens. Nothing happens until I come to the phase boundary, and then it snaps. Now, when I go back, it doesn't snap at the same line. So I go back. It doesn't snap at the same line. It snaps at the other line. Now, this is hysteresis. That's the usual hysteresis that we know. And all you need to demonstrate this is these two rubber bands and a little wheel. Okay. Oh no. Where is my laser pointer? I need the laser pointer because maybe not everybody has seen that. Let me give you another example of hysteresis, perceptional bifurcation. Okay. Look here. What do you see? A girl, a woman, right? Everybody sees the woman. Now look here. What do you see? A guy, a face of a guy. Everybody sees the face of the guy? Now look here. You can actually switch between the woman and the face. Can you do that? Now look at her again, okay? This is easier for the guys to go this way than the other way. So you see the girl, you see the girl, you see the girl, you still see the girl. You still see the girl. Oops, you see the guy, the face of the guy. Right? And now you go back, you see the guy, you see the guy. You still see the guy. That depends a little bit if you're a boy or girl, I guess. And then if you go to the other side. So what do we call this? Well, what do I call this? Not non-equilibrium phase transition, non-equilibrium phase transition. There's tons of these examples. For example, this is, can you see two faces here? Consider the black. You can also look at the white thing here that looks maybe like a chalice or something, like something you can put flowers in, right? Okay, let's get serious again. Let's do this business for our switch, okay? So we wrote down a population competition model for 3 of the amplitudes on the ring. And we wrote down a potential that actually basically kind of mimics the real equations that we have. It's not an exact map, but it mimics the real equations that we have. And this potential is, of course, a little bit more complicated. Now, with this, we then look at phase diagrams. And so they can, for example, plot a phase diagram, hexagon stability versus anisotropy, and so you don't have to read all the details here. I indicate the things that I want you to focus on. As a function of the induced anisotropy, we can either have a hexagon, which doesn't see much anisotropy, or if we make the anisotropy really big, then we get a two-spot pattern in the direction of that anisotropy. Maybe more interesting is this switch business that I talked about. So we have 1 and 2. We have directions 1 and 2. And so here's the phase diagram for these directions. Again, this is kind of complicated, but I'm telling you that if you go from this point where 1 is stable to this point where 2 is stable, you do the switch. And it will not surprise you then anymore that if you go back and forth, you have hysteresis phenomena. When I saw this, I said, well, this cannot be right. You look, I mean, have you ever seen a curve like this? I mean, it just ends there in somewhere, in nowhere land. I said, this must be wrong. But of course, I was wrong. Of course, the students know that much better. So the thing here is we have only 2 control parameters. We have really 3 control parameters. And so if you look at this with 3 control parameters, this makes a lot more sense. So this is the surface, the bifurcation surface, the bifurcation set in 3 dimensions, where the source and the hexagon stabilization and the anisotropic self-saturation here are all 3 control parameters. And then we have this bifurcation set, which is called elliptic umbilic singularity. And so that makes a lot more sense, I think. Because now you see where these, you make cuts through this, and all of a sudden something ends at, if you make a cut through this here, then all of a sudden this line ends wherever you make the cut, and you get funny looking curves. But in a larger space, it's not that funny looking, really. Yeah, we have a new comp exam order. And now the comp exam for the graduate students now in the future will require that every student is able to indicate some areas of physics that are related to what he or she is doing. And then I thought to myself, oh man, I'm in trouble, because I mean, with all this phase diagram business and equilibrium and non-equilibrium phase transitions, I would fail the comp exam. I cannot say what does that have to do with what geometric optics or so. There's just no way, Jose, I would say, but Jose is not here, I guess. So are there applications of catastrophe theory in other areas? And so I looked it up, and the first example was actually an example, not an optic example, and maybe you want to guess, or maybe you guessed it already. Let me tell you, I think most of you guessed it already. It's pretty obvious. Bulimia. Bulimia. There is actually papers out on the application of this catastrophe theory on anorexia nervosa. And I will not answer any questions about that because I don't know anything about that. I thought it was just interesting to see, oh, there's really far out stuff there. But again, coming back to, I mean, how can I tie in all these phase transitions and stuff to, say, geometrical optics? You know, would I ever pass the exam? And so I had a hard time with that because I just don't drink very much coffee, and it almost never rains in Tucson. Did you get that? Masoud is thinking now he really snapped. What are you on? I drank half a bottle of Dayquil today. No, so coffee. Once I realized, and Starbucks doesn't work for this, okay? Stace knows that, of course, what I'm getting at. Coffee. So applications of catastrophe theory in optics, real optics, coffee. Caustics in the coffee cup. You see this? You have a cup in the cusp, a cusp in the cup, a caustic in the cup, in the coffee cup. The caustics are lines that are tangential to all the rays, okay, and where the intensity is really big. And so people in geometric optics, most of you know this probably much better than I do. And those happen not only in the coffee cup, they happen also in the rainbow. That's why I said, well, if it just doesn't rain often enough to think about the rainbow all that much. It happens in the rainbow. The rainbow has a lot of theory papers. I found it interesting. I just copied this here, not because I know anything about so he talks about the cusps here. I found it interesting. This is from the University of Arizona in 1962. We haven't heard so much about the 50th anniversary of the College of Optical Sciences, and this is actually proof that there was optics here before the College of Optical Sciences. Yeah, so nowadays people talk about this stuff, the caustics, as diffraction catastrophes. Diffraction catastrophe, when I say that word, I'm not referring to the diffraction course 505, the course 505. That's not what I mean when I say diffraction catastrophe. I mean caustics. And so the person who was actually instrumental in this was Michael Berry. He actually put together the concept of caustics and catastrophe theory. And he found that actually these caustics are bifurcation sets, and the role of the control parameters in this case is played by the three variables x, y, z, the three space variables. And so then he was able to tell us all possible caustics, because he knew all possible bifurcation sets that can occur with three control parameters. And that's quite remarkable. And he actually, lo and behold, there's one example where he shows this kind of elliptic umbilic as a caustic generated by some lens. And again, I'm sure you guys know much more about that. I wanted to show this. Oops. let me see, what time is it? I want to spend the last 5 minutes to talk about this matrix element business. So this is a little bit more formal. It's maybe not a lot of fun, but I think it's of fundamental importance. And so this is about the interband dipole matrix element. So the question here is the following: we have a semiconductor valence band conduction band. We have a dipole matrix element. This is a dipole ER, and we have a momentum matrix element P. How are they related? It's a good question, right? It's in particular a question that is in one of the homeworks in Opti 507, and I know nobody ever likes this. So the homework basically for an atom is not that difficult to do. So if you have an atom, we use this the commutator between P that relates momentum and displacement operator via the Hamiltonian. That is non-negotiable. That's always right. Okay. And so if we have this commutator relating P and R and look at the matrix elements, we can just write out the commutator, HR minus RE, and then H acts on 1, this H acts on 1, and this H acts on 2, and then we get E1 minus E2, the energies of those states, and that's the relation between the dipole and the momentum operator. There's nothing difficult about this. The thing is that atoms have localized electronic wave functions that are normalizable. Now, if you have an infinite crystal, the thing is not quite so simple, because you have these wave functions that are everywhere, and those are not normalizable anymore, except to delta function. And delta function is really a pain to do this. So what we like is to have periodic boundary conditions to divide our infinite system into kind of finite systems where each finite system is actually the same. It's just copies of each other. And therefore, we have an infinite system made up of a bunch of finite systems. In this case, the wave functions are normalizable because they don't extend. They extend only from here to here, say, but they don't go to zero at the edges, in contrast to atomic wave functions. And so if we then look at this relationship in crystals, then we can ask ourselves, is this relation still true? And we can operate with the operator H on the right state, which is the valence band state. In this case, we get an energy out. But we cannot operate with the operator H on the left state, which is a conduction band. We do not get the energy out. And when you talk with people, everybody says, yeah, I know about that somehow, but you never find anything in the literature which actually does that. So we just thought, oh, we do this. Okay, so we wrote down the correction term. It's straightforward to write down the correction term that you get. This is the correction term. Never mind the details of this. It's just some term. And so the funny thing here is, or the important thing is, that this term and this term actually depends on how I place my unit cell in the crystal. And so the left-hand side does not depend on the location of the unit cell, but the right-hand side does. In contrast, if you start out with an infinite crystal, you don't have this correction term, but you have another very unfortunate thing. The matrix elements are not, you cannot assign numbers to the diagonal matrix elements. They are distributions in a mathematical sense. They are delta functions. Very unpleasant. You can never say what the diagonal matrix element is. You can never say the dipole matrix element R is 5 angstrom or something like that. It just doesn't work. And so we have looked at this for gallium arsenide, and we found, if we just focus on this, the dipole matrix element in gallium arsenide is about 0.3 or so angstrom at the maximum that we ever get by changing locations of the Wigner side cell. Whereas P, the momentum matrix element, is about 6. So there's almost a factor 20 difference. That means that the correction term is actually almost 20 times larger than the original term. And so that's one should be aware. It's quite different, actually, if you do terahertz spectroscopy. If you do terahertz spectroscopy with inter-subband transitions, everything is nice and very pleasant. So here we plot the correction term, and we plot all the quantities the correction term is in blue, the dipole is in red, as a function of the position of the unit cell. And if we place the unit cell such that the edge of the unit cell is just in the barrier of the barrier well material, then the correction term here goes to 0. And the dipole matrix and the momentum element, so this is 0 here, and the dipole matrix and the momentum matrix element are the same. There is no correction term. And so if you talk with people who do like, in general, one-dimensional system, they don't have this problem. Maybe they are not necessarily aware of that they don't have the problem, but they don't have the problem. So yeah, I want to skip this. So we published a paper and we put a very kind of, I would say, kind of comprehensive list of all possibilities that are out there and are known, at least to us. That if you ever want to go into more detail, this Hawk, by the way, is not the same Hawk as I had listed before as a co-author on the Deng et al. Paper, and that is not the Hawk that Stefan Koch. This is Albert Hawk, a different Hawk. He wrote a thick book, Semiconductor, very, very good book actually. But unfortunately, he proved this relation. Unfortunately, the proof was wrong, and took us a year or so to find where the mistake was in the proof, because once somebody proves something, it's not so easy to find why is it actually not right. So the summary. This is my summary. We started out with very fundamental things, like we started out with the electron-electron interaction, and we started out with the electron hole creation via the electric field, via the optical field, and then we found we could make excitons, bound states out of that, and then in the next step we said we can actually make correlated exciton states, or two exciton states, or bound exciton states. And then we discussed four-wave mixing, in particular four-wave mixing instabilities and correspondingly patterns. And in the end, we ended up with something very funny looking, like this elliptic umbilic bifurcation set. So this is basically my little journey through the universe of semiconductor optics. Here's gallium arsenide. And now I forget, is this the end? Let's see. Thank you.
So when you change your title, Professor Kolesik told me that he wants the refund. So